Hey guys, what's up people? Welcome to the session. I hope that all of you guys are doing good and taking care of yourself. So today is another day and I'm back with another one-shot video. I don't know how long it's gonna go, but then yes, it is a one-shot video of refraction through a lens. So today people, I'm in the office, so the background is gonna be a little different and you might see some discrepancies and all, like the video might be a little weird with a lot of flutters and everything, but I couldn't do anything about it people. But nonetheless, welcome to the session. My name is Anoop and yes, welcome to yet another one-shot series of refraction through a lens. So without wasting any more of your time, let's go through the entire chapter of refraction through a lens. The whole chapter we're going to do it in 1 hour, so make sure that you stay till the end and do not forget to subscribe to the channel and hit that like button as well guys. So with that said, let's start with a quote for the day. Now the quote for today is this guys: struggle leads to success. Now there's this saying that no pain, no gain. It's exactly like that. As long as you don't struggle in your life, as long as you don't experience the pain, as long as you don't experience how it's like to, have some sort of resistance in life, you will never understand the true, taste of success. That is what is actually the truth. It's actually the truth. It's not just some saying. You'll actually experience this as you go ahead in your life as well. So without wasting any more of our time, let's begin the topic for today. We have a lot of things to cover, starting from lenses and its components to refraction through a lens and its focus, action of a lens as a self prism, and principle rays of refraction, the principal rays of a ray diagrams of concave and convex lenses, sign convention, lens formula, magnification of a lens, numericals of on lens formula and magnification, and power of a lens and its application. So basically people, to complete all of these, we have taken about 7 hours. Right, to complete all of these topics, we are taken about 7 hours. And in today, I don't know whose blessings we're going to need, but we'll be doing the entire thing in 1 hour time. We're going to complete everything that is important from this chapter. So without wasting any more of our time, let's begin. Now, there are two types of lenses. First of all, let me tell you what is a lens. A lens is a transparent medium or a material which allows the light to pass through them, and as it's doing so, it happens because of the because of the fact that a light undergoes refraction when it's passing through a transparent medium. So there are two types of lenses. You have your convex lens and then you have a concave lens. So what's the difference between them? Let's start with the basic stuff. So the convex lens, concave lens is one which is thin in the middle and thick at the edges. So this is also called as a diverging lens. Now if you do not know why it's called as a diverging lens, don't worry, I've already covered people. Just wait for a couple of minutes and I'll tell you what is the reason for this. When we talk about a convex lens, on the other hand, a convex lens is something which is thick in the middle and thin at the edges. Now there are different types of concave lenses. You have biconcave lenses, plano-concave lenses, convexo-concave lenses, which is basically a combination of both concave and convex lenses as well. Then you have convex lenses, which are basically thin in the edges and thick at the middle, just the opposite of a concave lens. And again, here also you have concavo-convex, plano-convex, and biconvex lenses as well. So all of these, again, it's pretty much the same thing, but then yeah, just the terminology might be a little jumbled up. Now, a lens is actually a part of two different spheres. So if I imagine two different spheres, basically that is what, if there is, if they like a Venn diagram and they intercross each other, that is how your convex lens is formed. And if there's a gap in between these two these two circles, these two spheres of glass, then you will find a concave lens. So there are different parts of a lens, alright? So you have the center of curvature, the radius of curvature, the optical center, aperture, and principal axis. So what is the center of curvature? Like I told you people, our lens is actually formed. For example, if you talk about a convex lens over here, it's a part of it's a part of two different spheres. So like I told you, like a Venn diagram, when it's overlapping each other, that is how a convex lens is formed. So that sphere, the center, basically a sphere is a 3D triangle, that's what it is, right? So it has a center then. So the center of the sphere is what is called as the center of curvature. So basically guys, in a lens, you'll have two center of curvature because there are two different spheres which are overlapping, or maybe they might have a gap in between. In other words, there is two different spheres involved, and hence it'll have two center of curvature, one on the left hand side of the mirror, the lens, and other on the right hand side of the lens as well. Now, the distance from the center of the lens to the center of curvature is called as the radius of curvature. It could be from the center of the lens, or it could be from the center of curvature to any other point as well, because what is radius? Radius is nothing but the distance from the center, and it's going to be equal in the case of a triangle, in case of a rectangle, triangle, in the case of a rectangle. In the case of a circle, that's how it is. My God, okay, I'm out of my mind. So anyway, so in the case of a circle, that's how it is. So people here it again. So that is what is your radius, and here again. So that distance from the center of this center of the lens to the center of curvature, that is what is called as your radius of curvature. Or you can say that the radius of the sphere of the lens is also what is your radius of curvature, represented by capital R. Then you have the optical center. The geometric center of the lens is what is called as the optical center. Now, for example, if you talk about a circle, the geometric center is the center itself. Like in the case of a rectangle, if you talk about it, if you draw the diagonals, the point that it means, that is a geometric center. So here, the geometric center of that particular lens is what is called as the optic center. Alright, both for concave as well as convex lenses. Right, moving on. The next one is the aperture. Aperture is nothing but the complete refracting surface. In other words, wherever the whole surface where light can fall and undergo refraction, that is what is called as your aperture. So bigger the aperture, it can collect more amount of light. That means you'll have a brighter, better image as well. So you'll probably heard that in your recent phones and all, like 1.2 aperture, 1.3 aperture and all that. So that is what it tells you. The aperture tells you how much amount of light it can gather, because obviously it's a complete refracting surface. So the whole surface, so this whole surface, for example, if this is the object somewhere over here on this side is the object. So this is your aperture of the lens. So the complete refracting surface where light can fall and get refracted, that is your aperture, right? So both for concave as well as the convex lenses. Moving on, the next one is this people, that is the principal axis. So principal axis is nothing but it's a straight line which joins both the center of curvature, so passing through the optic center of the lens and passing through both the center of curvature. That line that we draw, that is called as the principal axis. So that, my friends, is all the terminologies that you have to be aware of when it comes to your lenses. Now, the next thing I'm going to talk about is super duper important, because this is super important. That's right. Focus of a lens. What is the focus of a lens? Let's take an example. Imagine I have a convex lens. Very simple. See does have a convex lens. Let's say a ray of light is coming and incidenting on the first surface, that is over here. And what happens? It gets refracted because it's passing from a rarer medium into a denser medium. So obviously there's a change in mediums happening. So yes, there'll be refraction. So what happens? The path of the light slightly changes. Once again, once it reaches the second surface, as the ray of light is leaving from the glass into the air, once again, because the medium is changing, again it undergoes refraction, and hence the ray of light gets refracted and moves this way. Now, if I were to draw a normal to the surface, now imagine this is a curved surface, not a straight surface, not a straight, I know it's not like a straight surface, and normal would look perpendicular. That is how the normal is supposed to be. This would be a normal then. But then here it's a curved surface. And because it's a curved surface, the normal that you draw would apparently look like this. So this normal would pass through the center of curvature of that lens. Alright, so why is that so important? Let's take another ray of light. Try to understand this, alright? So you see that one ray of light is passing through the principal axis. It's cut, it's like crossing one or the other point, or touching one of the point in the principal axis. Once again, I take another ray of light. Once again, the exact same thing, undergoes refraction once, undergoes refraction once again, and then again cuts through the principal axis. Now what you notice is that both those rays of light will meet at the exact same point on the principal axis. Again, why is that so important? You take n number of rays like this, 10, 20, 30, 40, 50, 100, 200, how many ever rays of light you take. If all of those rays of light are parallel to the principal axis and comes and coincides on the refracting surface of the lens, all of them undergoing the refraction will end up meeting at the exact same point itself. And that point where those rays of light meet or coincide after refraction, that is called as a focus. That is called as the focus of a lens. And because in the case of a convex lens, all the rays of light are converging or meeting at a particular point, they're all getting converged, they're all diverging and meeting at a particular point. That's why this lens, the convex lens, is called as a converging lens. Why? Because they're all meeting at a particular point. That's it. So that is what is your focus, the point of convergence. the point where all those rays of light meet, that is your focus. But the same goes with, see, it's not like it is only like if the rays of light are coming from only from the left, this happens. No, if the rays of light are coming from the right, also the exact same thing happens. Once again, all those rays will undergo refraction, and again they will meet at a point on the principal axis itself, and that would be the focus on the other side. And hence, for a lens, you don't have just one focus, people. No, you have two focus, one on the left and one on the right as well. And that is why plural of focus is nothing but foci. So you have two foci, each on one side. Simple. So you have two center of curvature and two foci, and then you have the optical center, all lying on the same line, which is your principal axis. Isn't that easy? It's damn easy, people. Alright, next one is nothing but a concave lens. The exact same thing, but in a concave lens, people, it's a little different. There's a little different. It's a little different. Why? Because the rays of light are not actually meeting. Alright, so what happens? It undergoes refraction, goes away, because again, it's traveling from a rarer medium into a denser medium. It goes towards the normal. So here the normal would actually look like this one. So the normal would be this. This is how the normal would be. So it's moving towards the normal. And once again, when it's going from rarer medium into denser medium into a rarer medium, it goes away from the normal. So again, the normal from this surface would actually look like this one. So this would be a normal over here, again passing through the center of curvature. So you see that it goes away from the normal, and again here the rays of light are going away, they're diverging away from one another, and that's why a convex lens is called as a diverging lens, because no matter how many rays of light you take, they will all diverge away, they don't meet at a particular point. But if a person is seeing from one side, what you notice is that these rays of light appear to emerge from this particular point. It appears to emerge from that particular point, and that there in a convex lens, in the concave lens, sorry, is the focus of that lens. See, in a converging lens, like in the case of a concave lens, sorry, in a convex lens, the rays of light are actually meeting at a point. Alright, so you can call that as a real focus, right? Because the rays of light are actually meeting. But in the case of a convex lens, sorry, concave lens again, no. In the case of a concave lens, the rays of light are not actually meeting, but they're appearing to meet, and hence it is called as a imaginary focus, or we can call it as an apparent focus, because it's not exactly real. The rays of light are not actually meeting. And the same goes over here also. No matter if the rays of light are coming from the left or from the right, it does not matter. Again, you'll find the focus, but on the same side as that of that particular where the rays of light are coming from, wherever the object is, on the same side you'll be able to find out the image as such. The image is actually formed over here in the case of a concave lens. Right? So here you can call it as a virtual focus. It's not exactly imaginary. The terminology that I used was wrong. It's a virtual focus, but here it's a real focus, and it's a converging lens over here, and this is a diverging lens. And that difference is your concave and convex lenses. Now, let's talk a little bit about focal point and focal length of a convex lens. So focal point is nothing but the point, you already know that, the focal points, there are two focal points, f1 and f2. f1 is on the left hand side and f2 is on the right hand side in the case of a convex lens. And you see that that is the point where the rays of light will converge and meet or form a particular image when the rays of light are parallel to the principal axis, and that is nothing but the focus. In the case of the concave lens also, it is the exact same thing. So here the f1 is actually on the left hand side, sorry, the right hand side, and f2 is on the right hand side. So remember this, guys, the image is always formed at basically in the case of a convex lens, it's formed on the if the rays of light are coming from the left hand side, then it will be formed on the right hand side. So basically it will be formed at f2. Now in the case of a concave lens, f1 is on the left hand side, right hand side, and f2 is on the left hand side. So the image, if the rays of light are coming from the left hand side, it will be formed on the left hand side itself, which is nothing but f2. Right, so it's just the opposite. Right? So naming, I'm trying to talk about the naming over here. You see this? So f1 is on the left hand side, and there it's on the right hand side. f2 is on the right hand side. But in the case of a concave lens, f2 is on the left hand side and f1 is on the right hand side. So you can clearly see that that is the only thing that you have to take care of when you do your ray diagrams. So imagine, like, see, generally we always keep the object on the left hand side itself, right? So imagine that the image is always formed in f2 itself. The thing is that image is always formed at f2, that is the focal point 2 itself. So that way it's easier to remember. So please make sure that you don't make mistakes over there as well. The last thing I'm going to talk about is the focal plane related to focus again. Focal plane is nothing but a 2D figure. It's nothing but a 2D figure. So a focal plane is nothing but a 2D figure, or you can say it's a plane passing through the focal point of a particular lens. And again, it's going to be perpendicular to the principal axis, because you're inserting a plane and the principal axis is going this way and the plane is this way, so it's going to be perpendicular to the principal axis. Same goes to the second focal point also. It's a focal plane. Again, it's a plane inserted to the focal point, and again, it's going to be perpendicular or normal to the principal axis as well. Alright, so let's do some quests. We'll be having a lot of questions also in between, so make sure that you're solving these questions as well, people. So here's another one question for you guys. Convex lens is also termed as converging lens. Why? Because any incident ray of a convex lens is bent towards the principal axis. Any incident ray of the convex lens passes passed through undeviated. Alright, any incident ray of the convex lens is bent away from the principal axis, or none of these. Why is convex lens is also termed as a converging lens? I'm going to give you 5 seconds. Pause the video and try to answer this by yourself. Just at least in your mind try to answer the question. But anyways, I'll tell you the answer in 5, 4, 3, 2, 1. It will be option number A, guys. That is, any incident ray in the case of a convex lens will bend towards the normal and meet at a point on the principal axis itself, and that is why that is where the focus is going to be. Now, alright, so all this while we've been talking about a simple convex lens. What if we were to change or imagine the lens as a set of prisms put together? Now, what do we mean by that? Imagine I have a convex lens. Now, a convex lens geometrically can be divided into 3 sides or 3 shapes. The one on the top is a triangular prism. The one in the middle is a rectangular prism, or you can say a rectangular glass slab. Yeah. Why to confuse yourself? Yeah. It's a rectangular glass slab. And the one on the bottom again is a prism, a triangular prism. Now, in a prism, we know that the rays of light after refraction will bend towards the base. So in both the cases, that is 1 and 2, that is A and B, the prism 1 and prism 2, that is the triangular prism 1 and triangular prism 2, it will bend towards the base and again meet on the focal point or form the focus of that particular lens, or is going to meet at the focus of that particular lens. If a ray of light is incidenting normally to the rectangular slab, it will pass through undeviated. So that ray of light will be passing through undeviated through the principal axis. So using this, all these rays of light will again meet at a particular point, and that point is nothing but the focus. Now, if you talk about a concave lens on the other hand, again, we can divide this into 3, but this time we don't have triangular prisms, we have trapezium prisms. Alright, the first one and the second one, the one on the top, that is a trapezium, that looks like a trapezium, right? So you have a trapezium prism on the top and a trapezium prism on the bottom, and then you have a rectangular glass slab in the middle. Now, once again, in a prism, they will always move towards the base. So in both the cases, you can see that the rays of light would bend and move away from the principal axis. But the second one in the middle, that is the one in the middle, that is your rectangular glass slab. When a ray of light incidents at 90 degrees, it will pass through undeviated without any sort of deviation whatsoever. Once again, here if I trace the steps back, it will appear to meet at a particular point. The same goes over here as well. It will appear to meet at a particular point, and that point is the focus of this particular concave lens, right? Alright guys, so yes, that concludes the first part of the topic. We have done a little, I think about 25% of it. We have a lot more to do, but that is the first 25% is already done. Let's get into the principal rates of a ray diagram. Now, these things that I'm going to talk about is super duper important. If you are still confused about ray diagrams, this one thing is definitely going to save you a lot of marks and a lot of beatings also. Because if you end up getting less marks, your parents will be waiting there with a bamboo stick Yeah, because they also like playing cricket when they were kids. So make sure that, I don't know about these days, but that is what I used to get. I don't know about you guys. Maybe you guys, times have changed, and your parents don't like play cricket on you, but maybe maybe not. But if you are, or if you're not, does not matter. If you want to be, score good marks, this is one thing that you have to understand. Principal is of a ray diagram. There are three things that are there. If you talk about a convex lens, a ray of light parallel to the principal axis after refraction will pass through the focus. This is the first standard incident ray. The second one, if the ray of light is passing through the focus, it will pass, after refraction, it will become parallel to the principal axis. And for the third one, if the ray of light is passing through the optic center, it will pass through undeviated. Alright, so once again, if the ray of light is parallel to the principal axis after refraction, it will become it'll pass through the focus. If it's already passing through focus, then after refraction it will become parallel to the principal axis. And thirdly, if it's passing through the optic center, it will pass through undeviated. That's it. So if you talk about a concave lens also, it's pretty much the same thing. Once again, here it appears to me through the focus, not that it actually does, but it appears to me through the, or passes the focus. And so if ray of light is passing through is parallel to the principal axis, it'll, after refraction, it'll appear to pass through the focus. If the ray of light is already appearing to pass through the focus, after refraction it'll pass through it'll become parallel to the principal axis. And if a ray of light is passing the optic center, it'll pass through undeviated. These are the three standard incident ray, and with these three things, people, you can draw any ray diagrams. Any ray diagrams can be drawn by using just these standard incident rays. Don't worry, I'll be talking about it later on. Don't worry about it. But before that, people, let's solve another question. Here's another one for you guys. A ray of light passing through a principal focus or appearing to meet at the principal focus after refraction will emerge parallel to the principal axis, parallel to the principal focus, parallel to the principal axis, perpendicular to the principal focus, or perpendicular to the principal axis. What do you think? A ray of light passing through the principal focus or appearing to be passing through the principal focus after refraction will emerge parallel to the principal focus, parallel to the principal axis, perpendicular to the principal axis, or perpendicular to the principal axis. Perpendicular to the principal axis, yeah. Focus and principal axis, yeah. The answer is in 5, 4, 3, 2, 1. It's going to be parallel to the principal axis, not principal focus, but parallel to the principal axis. All right, people. The most awaited topic of all. Ray diagrams of concave and convex lenses. Finally we are here, people. This question, I can't stress how important this is. How important this is something that I can't even stress on. Super duper important. Like, it's very important. So let's talk about it. Ray diagrams of concave and convex lenses. So guys, once again, if the object is placed at infinity, that means the rays of light are coming parallel to the principal axis and it will incident on the lens. So after refraction, because they are all parallel to the principal axis, according to what we just, the standard incident rays, if the ray of light is parallel to the principal axis, what's going to happen? After refraction, it will pass through the focus. So here also is the exact same thing. It will pass through the focus, and hence the image is going to be formed at the focus. And the size of the image is going to be, it's going to be a point-sized image. It's going to be a point-sized image. It's going to be small. It's going to be diminished. It is going to be real, and it's going to be inverted as well, because real images are always inverted. That's it. That is the answer for the first one. This is your first ray diagram. If the object is placed between 2f1, that is your center of curvature, 2f1 is nothing but your center of curvature, and infinity, in that case, the image is going to be formed between f and 2f1, that is between the focus and the center of curvature. Why? Let's answer that. Imagine one ray of light parallel to the principal axis after refraction will pass through the focus. That's what happens. So again, if you know the three standard incident rays, and out of the three standard incident rays, you just need to remember these two, this one and this one. If you remember just these two, people, you can solve any ray diagrams. Trust me, you can solve any ray diagrams by yourself. You don't have to by heart it. You don't have to do anything about it. You will do it by yourself. So one ray of light parallel to the principal axis after refraction passes through the focus. Another ray of light passing through the center of curvature, which is the optic center, passes through undeviated. So both of those rays of light will meet at a point between the focus and the center of curvature, or F1 and 2F1, sorry, F2 and 2F2, and that is where the image is going to be formed. So look at the size of the image. It's going to be diminished. It's going to be a diminished image. It's going to be real, and it's going to be inverted as well. This is the properties of the image as well. The third one, if the object is kept at 2F2, then the image is going to be formed exactly at 2F2 itself, of the same size, but it's going to be real and inverted. Just look at this. One ray of light after parallel to the principal axis pass through the focus. Another ray of light passing through the center of curvature, optic center, will pass through undeviated and again meet exactly at 2F2. What are the properties of the image? It is of the same size as are the object. It is going to be real because the rays of light are actually meeting, and it's inverted as well. Voila. If the object is kept between 2F2 and F1, in that case, our first ray of light will pass through the focus, another ray of light will pass through the center of curvature, but this time the image is going to be formed beyond 2F2. The image is going to be formed beyond 2F2, and the image, if you look at the size of the image, it's going to be magnified, much more bigger than the object, real and inverted. If the object is kept at the focus, the rays of light, one passing to the principal axis, parallel to the principal axis, after refraction will pass to the focus, one more passing to the optic center. But look at this. They are both parallel to each other. So we are assuming that the image is going to be formed at infinity over here, because the rays of light are not actually meeting at this point, but we are assuming that they are going to meet at one point or another later on. So that is why we assume that the image is formed at infinity. So size of the image is going to be magnified. It's going to be much more bigger than the object. Like you can see that it's much more bigger than the object, and yes, it's going to be real, and once again inverted. Right? The last one is between F1 and optic center. Now this is where it gets a little tricky. Majority of you guys go wrong in this one. So one ray of light parallel to the principal axis will pass through the focus. That's very clear. One more ray of light will pass through the optic center. Now you see this. Both the rays of light are moving away from each other. They're moving away from each other. So we are assuming that the rays of light are basically meeting on the same side as that of the object itself. So we are extending this, and basically they both meet at this particular point over here. That is why it forms a virtual image in this case, which is much more magnified, and it's going to be erect. Now this is the only situation in a convex lens where you get a virtual, magnified and an erect image. All the other times you'll get a real image, but here you're going to get a virtual image only in this situation. Alright, so that is about your concave lenses. So you see this, as you bring the object the closer and closer, the image size also becomes smaller and smaller. So that is from the focus to the optic center. You bring it closer and closer to the optic center, the image size also becomes smaller and smaller. But yeah, it will be still erect. It will still be a virtual image, but it's going to be it's going to form a smaller and smaller image as you bring it closer to the lens. So these are the properties. Now again, you don't worry about people. You can download the notes later on. So examples can be burning glass, that is your magnifying glass, camera lens, terrestrial telescope, slide projectors, collimator, and spectroscope. I've already talked about this later on. I mean, in the previous sessions. Don't worry about it. Magnifying glasses as well. Next one, people, is it's a quiz question. So here's another one for you people. The convex lens produces a real image of the same size as that of the object when the object is placed at 2F, at infinity, at F, or between the optical center and F. The convex lens produces a real image of the same size as are the object when placed at what distance? 5, 4, 3, 2, 1. The answer is at 2F, people. If you keep it at 2F, the image is going to be formed at 2F, and it's going to be the same size, real and inverted. Alright, so next thing we're going to talk about is the ray diagrams of concave lenses. So convex is done. Now let's move into concave as well. Let's finish it off. It's one of the smallest and one of the most easiest as well. Now remember, people, once again, going back to the principal axis, the principal, again, the the standard incident rays, not principal axis, the standard incident rays. We have seen that if the rays of light are parallel to the principal axis, after refraction they will appear to meet at the focus in the case of your convex lenses. So here the image is formed on the same side as the lens itself. Now again, is the the nomenclature is a little different given. So here they have actually followed the same nomenclature itself, that is F1 and F2. But in some textbooks they would have given this side on the left hand side as F2 and on this side as F1. So whichever, I would suggest you to talk to your teacher once about this nomenclature. Don't get it wrong, because don't lose marks on all these silly things. It's not exactly wrong, but why would you lose even half marks over these kind of mistakes that you can easily correct if you were to just talk to your teacher once. So make sure that you talk to your teacher and get to know which nomenclature is the best one to go with, and go accordingly with that. All right. So yeah, people. So once again, all the rays of light are parallel to the principal axis. So after refraction, they will appear to meet through the focus. So that is the first when the object is kept in infinity. When the object is kept anywhere from infinity to the optic center, from, let's say that from 2f2, beyond 2f2, or between 2f2 and f1, wherever the object is kept, every single time the image that you're going to get is going to be a virtual image, a smaller sized image, which means it's going to be a diminished image, and it's going to be erect as well. Every single time. This is the only thing that you're going to get. Every single time you're going to get the same thing. So one ray of light parallel to the principal axis after refraction will appear to pass through the focus. One more ray of light is passing the optic center, so the image is formed between F and the optic center, and you see the image, it's smaller, it's diminished, it's virtual, and it is erect as well. So you see this, as you bring it closer and closer, the image size actually gets bigger and bigger. In the case of a convex, in the case of a convex lens, people, as you bring it closer and closer, it becomes smaller and smaller. The image is getting smaller and smaller. But in the case of a concave lens, as you bring the object closer and closer, the image size gets bigger and bigger. But the image is always going to be formed between f1 and optic center itself. So these are the applications: Galilean telescope, and also the myopic eye. That is, the short-sightedness that you have, where people can see what's nearby and can't see what's far away. That is short-sightedness. So to correct that, we again use a concave lens itself, right? So this is your other question, people. The size of the image formed by a concave lens is always smaller than the size of the object, always greater than the size of the object, the same as the size of the object, or it depends on the position of the object. Such an easy question, people. 5, 4, 3, 2 are always smaller, no doubt. It's always going to be smaller than that of a concave of the image in the case of a concave lens. All right. So that, I believe that is 50%. That's almost 50% we have done. Now let's understand about sign convention. It's very simple, guys. Anything on the left hand side of the lens, concave or convex, does not matter, is going to be negative. Anything on the right hand side, concave or convex, does not matter, it's going to be positive. Anything above the principal axis, positive. Anything below the principal axis is negative. So if the rays of light are going with the incident ray, then it's positive. It's going against the incident ray, then it's negative. Above the principal axis, positive. Below the principal axis is negative, because the object is always kept on the left hand side, and that is why I'm talking about in terms of incident rays, but it's still exactly the same. So all distance are measured from O, that is the optical center. The distance along the incident ray is taken as positive. Distance opposite to the incident ray is taken as negative. Distance above the principal axis is positive. Distance below the principal axis is negative. That's it, people. So yeah, in the case of a convex lens, people, the focal length is always positive. So if in case in the questions also, do not ever forget this. It's going to be super duper important that you understand this, because we will be solving some questions, but you have to understand that yes, in the case of a convex lens, it's always going to be positive. The focal length is always positive, but in a concave lens, it's always going to be negative, because the focus is on the same side as that of the lens, so it's going to be negative, right? So that's how it is. So U is always taken as negative because it's always kept on the left hand side. For convex lens, F is positive. For concave lens, F is negative, right? So that is it, people. So yeah, guys, so that marks the halfway through now. Yes, are you guys enjoying the session? In the chat box, are you people enjoying? If you are, do not forget to hit the like button. Do not forget to subscribe to the channel, because we'll be coming out with lots of one-shot videos, lots of amazing stuff for you guys to make sure that you perform well in your finals and your pre-boards. So if you want to be a part of this and learn with the best of the best teachers and have a lot of fun and amazing sessions like this and gain 100% knowledge, study every single topic in depth before your final exams, this is your chance. Vedantu is here for you people. So all you gotta do is click on the link that is given in the description as well as the pinned comment section. I think I went too far, but yes, all you have to do is click on the link that is given in the description as well as the pinned comment section, and that is going to take you to the site of Vedantu. Now what is the importance? Why should you choose Vedantu? Let me tell you that first. See guys, in many of times it so happens that they might put a limit to how many sessions that you can see in one day. But at Vedantu, there is no such limit. You can watch unlimited live session, just like YouTube. No matter how much of videos you watch, they allow you to watch. There's no restrictions like that. So in the same way, at Vedantu also you can watch how many ever live sessions you want. And with that, have a lot of fun and have amazing quiz questions like this one, and compete with the rest of the world with the help of the leaderboards as well. So all these quiz questions, you'll have a leaderboard, so you can actually see your progress in the session, see how good you're doing. All of that is possible with the help of these sessions that you have. With this, even if you miss out a session, you can still take the quiz after that when you're going through because you get, for every session you get the replay. For those sessions also, once again when you're watching the replay also, you can again take the quiz and once again see the leaderboards of how, and check out whether you are improving in that particular class or not. And people, download all the premium content, all the handwritten notes, every single recording, all for free. Yes, you heard that right. All the handwritten notes. So what more do you want, people? Everything that you need is already covered. And with this, you don't have just one teacher in the live session. No. With the master teacher, you will also have the class teacher to help you out to clear every single doubt of yours. No matter how many it is, 200, 500, does not matter. All those 200 and 500 doubts will be cleared inside the session itself with the help of the class teachers. And I would say thing that you need the most at this point of time is practice and more practice. All those things will also be covered. You have unlimited tests and assignment, and these test questions are taken from your pre-boards, from your boards, from your Olympiads, from your NSOs, ISOs, pretty much every possible outlet that you can think of. All types of higher order thinking questions, things that you need for your board exams, every single type of question is covered in these tests and assignments. So you never have to go any place else. It's like a one-shop stop for everything that is related to education. And with this, people, 5,000 plus micro courses and crash courses, all for free. All you gotta do, click on the link that is given in the description as well as in the pinned comment section, and the coupon code, my coupon code is AMEPRO to avail the discount. So if you go for 1 month program, people, the base price of that is 2,699 rupees. If you use the coupon code AMEPRO, you get a discount of 500 rupees and the price drops on to 2,159 rupees. And if you go for the 5-month program, because your exams have been postponed to the month of June, so until June 21st, that is even after your exam is started, that is June 14th is your exam, is when your exam is set to start. So even after that, you will still get our effort, you'll still get our help as well. And that 5-month program would cost you about 7,200 rupees. If you just think about it, if you just take 2,000 rupees per month, 5 months it's 10,000 rupees. So you're getting more than 3,000 rupees discount for these next 5 months. And trust me guys, these 5 months are more important than what you've spent till this time that you already had. Right? So again, the link is given in the description as well as the coupon code is AMEPRO to avail your discounts. And once again, just think about it, people, in terms of sessions that you take. In that 1 month duration, you have taken about 200 sessions. That means that you have been paying just 11 rupees per session. And if you go for the 5-month program, you have attended about 1,000 sessions in those 5 months. That means that the price that you're paying per session is 7.2 rupees. That's less than a packet of Lays, which costs you 20 rupees and 80% air. right? So yeah, people, once again, it's for your own good. The link is given in the description as well as in the pinned comment section. Make sure that you check out the link as well, and the coupon code is AMEPRO to avail those amazing discounts. All right, last couple of things left out: lens formula, magnification formula, power of a lens. So these are the only topics that is left out here. I think we're done 75%, almost, not 50%, 75% is already done. A little bit more left and then we'll be done, guys. Lens formula. What is lens formula? Simple. 1 by v minus 1 by u is equal to 1 by f. That's all. That is what is your lens formula. So 1 by v is nothing but the image distance, 1 by u is nothing but the object distance, and 1 by f is nothing but the focal length of that particular lens. So both for concave and as well as convex. Now remember this, guys, u is always going to be negative because the object is always kept on the left hand side. Now if you talk about the object the image distance, it can either be positive or it can be negative as well, because it depends on where the image is formed. It depends on what type of lens you're using, so it depends on that. If you talk about the focal length, once again, if you talk about a convex lens, it's going to be positive. For concave lens, it's going to be negative. So these are the things that you have to take care of, because these signs will help you understand the whole how to solve your problems, because there'll be a lot of questions asked based on this, and if you get those signs wrong, you will end up losing a lot of marks as well. So don't forget that as well, guys. All right, so again, you have to use the same lens formula and you have to use the sign convention as well. So anything on the left hand side is negative, anything on the right hand side of the lens is positive, above the principal axis is positive, below the principal axis is negative. That's all right. So this is the question, people, to test if you guys have really understood the topic or not about the lens formula. Remember this, guys, mirror formula and lens formula slightly different. Mirror formula, it's 1 by v plus 1 by u is equal to 1 by f. In the case of lens formula, it's 1 by v minus 1 by u is equal to 1 by f. So this is a big difference. Do not get confused in this one. Write it in a sheet of paper, stick it on your mirror or something. See it every day so you never ever forget it. Alright, so this is the question. Go ahead and solve this. An object is situated at a distance of f by 2 from a convex lens of focal length of f. Distance of the image will be plus f by 2 plus f by 3 minus f, or minus plus f by 3 f by 4. Let's go, guys. Come on, let's see who solves it first. An object is situated, so object u is equal to minus f by 2. Focal length is taken as f itself. You have to find out what is v. That is what you're supposed to find out. So 1 by v minus 1 by u is equal to 1 by f. 1 by v minus of minus f by 2 is equal to 1 by f. So minus gets cancelled, so it will be plus. So 1 by v plus f by 2 is equal to 1 by f. Take this to the other side. So 1 by v is equal to 1 by f. Sorry, this will be 2 by f by 2 only, no? F by 2, right? So when it goes to the other side, it will be minus, wait, what? Okay, yeah, it's correct only. So it will be, this will be plus, so it will be minus f by 2. So wait a second, I think I made a mistake. Yo people, this is the mistake. It's 1 by u, people, so it will be 1 by f by 2, right? Sorry. So it will be 1 by f by 2, so that means that this will go to the numerator. So this will change into, sorry. So you can rewrite this as 2 by f, because it's 1 by f by 2. So when it goes to the 2 will go to the numerator and it'll be 2 by f, right? So 2 by f is what you're going to get. Then f is a common denominator, so you can write as 1 minus 2 by f. So 1 by v is equal to minus 1 by f. So 1 by f, yeah. All right. So what is v? V is equal to minus f. Yo, that is the answer for this question, I believe. Yo, that is the answer, people. That is the answer for this question. Sorry about that silly mistake that I made. Do not repeat the same mistakes that I make. So make sure that you remember that these kind of things also can go wrong. So make sure that you don't make the same mistake. I'm trying to set an example. That's what teachers do. We set examples. All right. Here's another one. That's how you cover up your mistakes. All right. The distance at which an object should be placed from a thin convex lens of focal length of 10 centimeters can to obtain a virtual image of double of its size is minus 5 centimeters, 5.5 centimeters, minus 10 centimeters, and 15 centimeters. Go ahead and try this question. Try the question out. Pause the video and try this question by yourself, people. Distance at which, so you're supposed to find out what should be the distance. So u is what you're supposed to find out. The focal length of a convex lens is taken as 10 centimeters, so it's going to be plus 10 centimeters itself. Now, you're supposed to obtain a virtual image double the size of the object. So they've given that m is equal to 2 because magnification is 2. It's double the size of the object. So I can, if you remember the formula, m is equal to v by u is one of the formulas that you have. So what is m? M is 2. 2 is equal to v by u. You do not know u. You do not know v as well. So solve the equation for v. V is equal to what? 2u. 2u is what you're going to get. So use the lens formula now. 1 by v minus अरे की हो गया? Once again people. की हो गया? Alright, once again guys, let me just write it down. Minus 1 by u is equal to 1 by f. 1 by v is equal to 1 by 2u minus 1 by v, u is equal to 1 by f. I just put the value of v in place of v, so put it as 2u. So into 2 to find out the LCM. So 1 minus 2 divided by 2u is equal to 1 by f. 1 by f is what? It is 10, right? F is 10, so why keep it as 1 by f? To keep it as 10 itself, 1 by 10. So you'll get it as minus 1 by 2u is equal to 1 by 10. So cross multiplication, minus 10 is equal to 2u. So u is equal to minus 10 by 2, which is nothing but minus 5. Voila, people, voila. That is the answer. Minus 5 centimeters would be the answer for this question. Moving on to the next one. The next concept is magnification. What is magnification? Magnification tells you by how much what basically tells you, magnification tells you how big or small the image is. That is what it tells you. Whether it's going to be big or whether it's going to be small. How big or how small the image is. That is what magnification tells you. And the formula to find a magnification is hi by h naught. That is nothing but height of the image divided by the height of the object, which is also equal to v by u. So if you remember in your mirrors, you have seen that it is minus v by u, but here in lenses it's plus v by u. So that is the only difference in terms of magnification formula of both lenses and mirrors. So here it will be v by u and hi by h naught is what is the formula. Sometimes you might have to use both, combination of both of these, that hi by h naught is equal to v by u. But yes, this is the formula guys. Magnification is equal to height of the image divided by the height of the object. So how much, by what ratio, what is the size of the image in comparison to the original object? That is what magnification tells you. Is it 2x, is it 3x? That is what magnification tells you. And it is equal to v by u. That is object distance, image distance divided by object distance. So once again, here also it's the sign convention would apply. If it is a real image, then it's going to be negative. Why negative? Because real images are always inverted. So in other words, inverted images you will have minus m, and if it's an erect image, which is generally a virtual image, will be positive. So that means height of the object, so the height of the image is positive, which means that m is also going to be positive, which means that the image is erect. If height is negative, then m is also going to be negative, and hence the image is going to be inverted, just like this one. So m is equal to hi by h naught. So if magnification is greater than 1, then it's an enlarged image. If it's less than 1, it's a diminished image. If it's equal to 1, then it's of the same size. Sign convention plus means it's an erect image, which is generally for a virtual image. If you see the plus sign, that means it's an erect and virtual image. If you see the minus sign for magnification, then it's an inverted and a real image, right? So this is your next question. People, go ahead and solve this one as well. An object of 9 centimeter from a magnifying lens and its image from a magnifying lens, and its image is formed by 36 centimeter from the lens. What is the magnification of the lens? Alright people, so magnification is equal to v by u. They've given v as 36 divided by 36, so that's going to be 4. Such an easy peasy question. The answer is going to be 4 people. That's such an easy question. All right, the last topic people, that's it. 0.1% left. Right? Let's say 1% is left out. That is the power of the lens. What is the power of the lens? See guys, the power of a lens tells you by how much can a lens bend the rays of light. That is what power tells you. So higher the power, more is going to be the bending of the light. Lower the power, less is going to be the bending of light. Now what do I mean by that? First of all, let me tell you the formula. The formula is very simple. Power of a lens is equal to 1 by f, half or 1 by the focal length of that particular lens, or reciprocal of the focal length. That is what it is. But the focal length should be in terms of meters, because the SI unit of power is diopter. So 1 by meter is what you have, the unit, and that is nothing but, or you can say meter to the power minus 1, which is nothing but diopter, which is represented by capital D. That is the SI unit of diopter, and only if the focal length is taken in terms of meter. If you take it in terms of centimeter, then you can't say it, but if you take it in terms of meter, so always remember to convert it to meters before you find out the power, because you're telling it as diopter, and when you're telling it as diopter, it should be in terms of meter itself. So power of a lens can be positive or can be negative as well. If it is positive, that means that the focal length is positive. If it's negative, that means it is the focal length is negative. And which lens has a positive focal length? Convex lens. And which one is a negative focal length? Concave lens. So for a convex lens, it's going to be positive. For a concave lens, it's going to be negative, right? And yes, people, like I told you, low power means, you see this, the focal length is going to be much more longer. So the bending of ray of light takes longer because it has low power. So longer focal length and less bending would happen. If the power is high, then the bending of ray will be much more, and the focal length is going to be much more shorter because it's able to bend the light immediately. In the case of a low power lens, it's going to take a little longer, so the focal length is a little longer, but high power lens will have lesser focal length. Right? Alright guys, so yes people, if you talk about a thin lens has low focal power, low power, which means that it has a very large focal length, and it deviates the ray of light also less. In the case of a thick lens that you have, it would have more power because it can deviate the light more, and more importantly, it'll have lesser focal length. Again, P is equal to 1 by F, so if F is more, it's going to be less. If P is less, then F is going to be more. So that's it. Indirectly proportional, that's what I'm trying to say. So what are the application of lenses? Objective lenses are used in your telescopes, cameras, slide projectors, and all of that. We use lenses. It could be a combination of both concave and convex lenses. Eye lenses for correction of myopic is concave lens. Like I told you, nearsightedness, you can see what is nearby, but you can't see what's far away. So use a concave lens for that. So the power is going to be negative over there. Hypermetropia is when a person can't see what is can't see what is nearby, but can see what's far away. In other words, farsightedness, and in that case, to correct it, we use convex lens. For magnifying glasses, we use convex lens. Collimator of a spectroscope, also we use convex lens itself. Eye lens of a Galilean telescope, also we use convex lenses. Lens to correct chromatic aberrations, also we use chromatic aberrations. Sometimes when you take an image, you get this, on the object, on the left of the object, on the right of the object, you might get some red lines or green lines and all that. That is what is chromatic aberration. This time, these days we use it as a filter, but that is what is called chromatic aberration. So those, to correct that also, we use lenses itself, right? And by that, people, the last question for the day. Let's finish it off with this question. Let's end it with a bang. Let's see how many faces were able to give the right answer for this one as well. If the lens has a focal length of 25 centimeter, calculate the power of the lens. Is it 4 diopter, 40 diopter, 0.4 diopter, or 0.04 diopter? The focal length, okay, they have not given me any space. All right, so focal length is equal to 25 centimeters. So convert that to meter first. So divided by 100, so that's 0.25 meters. So P is equal to 1 by 0.25, which is nothing but 4 diopter. That is the answer, people. That is the answer for the last question. And by that, please do not forget to subscribe to the channel. Hit that like button. I hope you enjoyed it. We completed the entire chapter, and I think in an hour. So yeah, make sure that you hit the like button as well. Thank you for joining, guys. I'll catch you guys in the next one. Take care of yourself. Stay safe. And until the next time, this is signing off. Bye bye, guys. Take care. Bye bye.